Number 9. A LC circuit consists of a 50 millihenry inductor and a 100 microfarad capacitor. What is the resonant frequency? So let's draw a circuit. So here's our AC source, and there is an inductor L and a capacitor C. So that's a typical inductor capacitor LC circuit. Now the equation to calculate the resonant frequency is 1 over 2 pi square root LC. So all we need to do to find it, to answer part A, is just plug in the data that we have. So we know the inductance, 50 millihenries is 50 times 10 to the minus 3 henries. And then the capacitance is 100 times 10 to the negative 6 farads. So all you got to do is type this in. But let's take it one step at a time. Let's multiply 50 times 10 to the minus 3 by 100 times 10 to the minus 6. That's 5 times 10 to the negative 6. If you take the square root of that and then multiply it by 2 pi, you should get 0.01405. And if you raise it to the negative 1 power, this will give you the resonant frequency, which is about 71.2 hertz. Now keep in mind, at the resonant frequency, XL is equal to XC. The inductive reactance is equal to the capacitive reactance. And in fact, using this expression, you can derive this equation. Let's go ahead and do that. So XL is equal to XC. XL is 2 pi FL. XC is 1 over 2 pi FC. Now what we're going to do is, let's multiply both sides by F. So on the right side, these two will cancel. On the left side, F times F is F squared. So we're going to have 2 pi L times F squared, and that's equal to 1 over 2 pi C. Now let's multiply both sides by 1 over 2 pi L. On the left side, 2 pi L will cancel. So we're going to have F squared is equal to 1 over 2 pi times 2 pi is 4 pi squared, and then times LC. So now let's take the square root of both sides. The square root of F squared is F. The square root of 4 is 2. The square root of pi squared is pi. And the square root of LC is just square root LC. And so that's how you can derive this equation. Now let's work on part B. What capacitance is required to produce a LC circuit with a resonant frequency of 1500 Hz if L, the inductor, is 15 millihenries? So let's start with this equation. And our goal is to solve for C. So let's begin by squaring both sides. If we take the square of both sides, we can see that the resonant frequency, the square of the resonant frequency, is equal to 1 over 4 pi squared times LC, which we had this equation not too long ago. So now what we're going to do is multiply both sides by C. And so on the right side, these will cancel. And so we have C times F squared is 1 over 4 pi squared times L. Now let's multiply both sides of the equation by 1 over F squared. So these two will cancel, and on the right, we're just going to multiply this by F squared. So we're not going to have F squared on the left side anymore. So C is equal to 1 over 4 pi squared times F squared times L. So that equation will help us to calculate the capacitance in an LC circuit at resonance. So the frequency is 1500 Hz, and L is 15 times 10 to the minus 3. So 15 times 10 to the minus 3 times 1500 times 4 pi squared. That's equal to 888.26. So 1 divided by that result will give us a capacitance of 1.126 times 10 to the minus 3 farads. 10 to the minus 3 is the same as milli, so this is about 1.13 millifarads. Or if you want it in microfarads, multiply by 1,000. That's 1130 microfarads. So that's the capacitance required to produce an LC circuit with this resonant frequency. Number 10. A 12-volt AC signal is connected across a RLC circuit consisting of a 50 ohm resistor, a 7.04 nanofarad capacitor, and a 900 millihenry inductor. Determine the resonant frequency of the circuit. So let's draw a picture. So we have a resistor, a capacitor, and an inductor. So the voltage is 12 volts. And the resistance is 50 ohms. Let's calculate the resonant frequency to begin. It's going to be 1 divided by 2 pi times the square root of LC. In this problem, L is 900 millihenries, or 900 times 10 to the minus 3. And the capacitance is 7.04 nanofarads, or 7.04 times 10 to the minus 9 farads. So you should get a resonant frequency of, if we round it, 2000 hertz, or simply 2 kilohertz. So let's put that here. Now let's focus on part B. What is the inductive and capacitive reactance at this frequency? So let's start with the inductive reactance, which is 2 pi F times L. So that's 2 pi times a frequency of 2000 hertz times the inductance, which is about 0.9 henries, or 900 times 10 to the minus 3. So XL is about, if we round it, 11,310 ohms. So let's put that here. We're going to say it's 11.3 kilo ohms. Now let's calculate XC. XC is 1 over 2 pi FC. So that's, in your calculator you can type like this: 1 divided by parentheses 2 pi times a frequency of 2000 hertz times a capacitance of 7.04 times 10 to the minus 9. So you're going to get also 11,304. I'm going to round that to 11.3 kilo ohms. So as you can see, these two are very close. If the circuit is perfect at the resonant frequency, the capacitive reactance should equal the inductive reactance. Now in this example, we have some rounding errors, but it's close enough. We can work with that. Now what about part C? What is the impedance and the current in the circuit? At the resonant frequency, the impedance is equal to R. So it's going to be 50 ohms. And here's how you know. We know that Z is equal to the square root of R squared plus XL minus XC squared. So this is going to be the square root of 50 squared. XL is 11,300 if we round it. XC is also 11,300. Because they're the same, XL minus XC is 0. So the square root of 50 squared plus 0, which is the square root of 50 squared, that's simply equal to 50. So, under perfect conditions, at the resonant frequency, the impedance is simply equal to R. So now that we have the impedance, we could find the current. The current is going to be the voltage divided by the impedance. So we have 12 volts, and the impedance is 50. 12 divided by 50 will give us a current of 0.24 amps. Now let's calculate the phase angle. So this is going to be arctan, or inverse tan, XL, which is 11,300, minus XC divided by R. So basically this is inverse tan of 0. Arctan of 0 is 0. So at the resonant frequency, the phase angle is 0. Now what is the voltage across each element? So we have a current of 0.24 amps. Let's use that information to find the voltage across the resistor, the capacitor, and the inductor. The voltage across the resistor is going to be I times R. So the current of 0.24 amps times the resistance of 50 ohms. And that's equal to 12 volts. So that's the voltage across the resistor. Notice that it's equal to the voltage of the source, because the other two voltages, they're the same and they're going to cancel out. Now to find the voltage across the capacitor, it's going to be I times XC. So that's the current of 0.24 amps times 11,300 ohms. And this will give you a voltage of 2712. Now, VL, which is I times XL, is going to give you the same answer. You have a current of 0.24 and an inductive reactance of 11,300. So you can get 2712 volts. Notice that the voltage across the capacitor and the inductor is very, very high. As you can see, it's significantly higher than the voltage of the source. The voltage of the source is only 12 volts. The voltage across the capacitor and the inductor is 2,700 volts. It's much, much higher. In fact, more than 100 times higher. So, very high voltages can be produced in an RLC circuit. So just keep that in mind.